All right, welcome. Happy Monday. Some quick review, but we're going to use what we did on Wednesday, I guess. I guess it feels like a long time ago. It was only Wednesday, but so in terms of review, right, we talked about changing the compounding frequency. Okay, so changing the compounding frequency. Okay. And from our formula sheet, right, that is this top section here. And maybe I'll keep the top as well, so you know where it's from. So this is on page 2 of your formula sheet. And so we went through, yes, that's the quiz, I think. Yeah. So for continuous, so I can't really see this without downloading it and opening it separately. So let's see here. So for continuous compounding, then if you're trying to find I2 and you're going from continuous to some compounding frequency, then you use this one. Whereas if you're going from some compounding frequency to a continuously compounded frequency, then you use this one. And those are all things that, so these I would say are all special cases from last day that we went through and talked about. Okay. But I also said that, all right, those are all good to know, but this is the one that we're going to focus on. Okay. And so these guys are kind of special cases. So the effective rate is that special case where we're moving to an annually compounded rate. Okay. And so here, let's just kind of highlight these. Okay. So the effective rate is a special case, which we don't actually need, okay, because we could derive it from this case or this case. Yeah. But it's the effective rate, so it's a special case where we convert to an annually compounded rate. Okay. Which means that F2 is 1. Okay. So it's a special case. Okay. And these ones, let's see here. These guys are a special case in the sense that they have to do with continuously compounding. Okay, so continuous compoundings. They're also a special case. Okay. So the IEFF is e to the r minus 1. What's that one doing? It's taking a continuously compounded rate and moving to an annually compounded rate. So F1 is continuous and F2 is annually, or let's say 1. Okay. I2 is e to the r over F2 minus 1 is when we're going from a continuously compounding rate to some F2. Okay, so F1 is continuous and F2 is F2 to show that F2 can be anything. So notice that this first one is just a special case of this second one. So you really don't need this first one. You can just use the second one, right? And you'll see if you let F2 be 1, then you get the same thing, right? So you don't really need all these formulas kind of clouding your judgment here. And then finally is when we're moving from some compounding frequency F1 to to a continuously compounded rate. So R is F1 times, the natural log of 1 plus I1. So F1 is some F1 and F2 is now continuous. Okay. So like I said, those are all special cases and they're good to have up our sleeves, but the one that we're going to be working with the most is this one. Okay. And so the one, we will use the most is I2 is equal to 1 plus I1 to the power of F1 over F2 and then minus 1. Okay, so that's the one that we're going to use the most, right? And what we're going to say is that F1 is going to be the compounding frequency. Okay, so here, F1 is going to be our compounding frequency. And F2 is going to be our payment frequency. So if they're not the same, then you have to make adjustments. Our payment frequency. Okay. So that's going to be super, super important. And I don't know if I can highlight this enough, but here, right? So this is what we're going to come back to over and over and over and over again. Okay, because now as part of our first step, so when we moved it from simple interest to compound interest, right, what did we do? We said, okay, wait, did I start? Oh, okay, I did start the recording. It just doesn't say anywhere. Okay, good. So when we moved from simple interest to compound interest, right, we introduced that kind of first step where, okay, now I don't need time. I need the time times the frequency, because now I need the number of compoundings. And instead of R, I need I, right, the periodic interest rate. And so now we've got an additional step. If you have regular payments, right, and I'll write that down in just a sec. If we have regular payments, right, we have an annuity. And so for an annuity problem, the first thing that we're going to do is just calculate I2. Okay. And so it's that extra step, right? And then we're kind of off to the races. So we introduced annuities. Which is when we have a series of regular payments, right? So car loan, mortgage, right? Retirement savings, etc. Okay. And that's all we said about annuities last day. And so today we're going to start section 6.2, which is called annuities. Okay. So annuities, like I said, are when we have these regular payments. Now, what's going to happen is there are a couple of different types of annuities. Okay? The one that we start with in chapter 6 is when the payments are made at the end of the payment period. Okay? The only change in chapter 7, and I mean the only change, is now the payments are made at the beginning of the payment period. Right. And so if you're making monthly payments, for example, on a car, then if you make that payment at the beginning of the month, that's going to be different from at the end of the month, right? Because you get a deduction in the amount of interest that you have to pay, right? Because you're paying it essentially a month early, right? And so it'll behave just ever so slightly different, right? And so that's where we'll get to in chapter 7. But for chapter 6, right, our payments are going to be at the end of the payment period. Okay. Just so we have a roadmap of the formula sheet. And this is kind of like your countdown to the end of the term, right? Because once we finish this formula sheet, there's nothing left for us to learn, right? Just kind of perfect. So we've already introduced all these formulas here. And in terms of let's see here. So let's see here. So we talked about these guys already, right? These were in section 6.1. Okay. This side here, all the way down to the perpetuity. And you know what? Maybe when do we introduce? Oh, I'm kind of, can't remember if we introduce perpetuities in chapter 6 or chapter 7. Perpetuities are super fun because you get payments forever. I'm just flipping through. I think it's in chapter 7. Okay. So then here, this side, oops, is all chapter 7. Okay. But notice that they're very, very similar. So chapter 6 and chapter 7. And then we only do one section, which is a special case of mortgages, which are annuities, right? But we're going to look at how do we break down a mortgage payment by payment. Okay. And so here, right, we introduce these formulas in chapter 6. Okay, so that's what we're going to start today. And then we do, if you kind of look across, right, there's really not that big of a difference in the formulas between the left-hand side and the right-hand side, right? And so that's the only change in chapter 7. And so, right, and we'll kind of talk about those. And then perpetuities are these bottom two, which are just kind of fun. Okay. And it's a fun idea too. All right. So annuities, right, is when we have regular payments. Okay. So just as a heads up, so in annuities, we have a regular payment amounts. PMT is how we're going to denote it. So PMT is the payment amount at some frequency F2. At some payment frequency Now I want you to get in the habit of calling it F2 because that's how we're going to see it in our formulas. Okay, and so that's why I want you to get in the habit of using F2. Okay, and so we have these regular payment amounts. Okay, now I'm going to draw a general timeline, You know what? No, I'm going to start like this. There are two types of annuities, okay? And I'm going to break them up into chapter 6 and chapter 7 because that's what the textbook's done, okay? But the same ideas apply, okay? So you can have two different types of annuities. You can have an ordinary annuity. That's when payments are at the end of each period. Payments are at the end of each period. If it's not clear, this is also the default. Okay. So if unclear, this is the default. Okay, so what I mean is if the payments are at the beginning of the payment period, then it has to be an annuity due, which is the other type of annuity. Okay, so here we can have an ordinary annuity or an annuity due. I use the due to remind myself that it's at the beginning of the payment period. So payments are at the beginning of each period. Okay. So the difference here is at the end. So this is chapter 6 and this is chapter 7. Okay. With only slight changes, right? So once we've tackled chapter 6, then once we get into chapter 7, we just say, okay, we see a slight change, but then all the questions are solved in the same way. Okay, just the formula changes slightly. Okay, and so what we're going to have is we're going to have some compounding frequency and some payment frequency. Okay. So in annuities, we will have a compounding frequency, F1, and a payment frequency F2. And a payment frequency F2. Now, if F1 is not equal to F2, right, then you need to calculate I2. Okay. But as a first step, right, I would suggest just always calculating I2. So as a first step, always calculate I2, where I2, right, is 1 plus I1 to the power of F1 over F2, and then minus 1. Okay. A lot of the time they're going to be the same, okay? But we need to catch it if they're not the same, right? And so that's why I want you to get in the habit of just writing them down immediately. Okay. In terms of our timelines, so the timeline for annuities is going to look something like this. Okay. So we're going to have maybe today, and then I'm going to take 5 years to pay off a car, right? And so I'm going to have regular payments of some amount. Now, we know how to solve this, right? But if I'm making monthly payments, which is very real thing, right? So that can happen, right? You make monthly payments to pay off your car. That's normal, right? And so what would we do? For 5 years, you would have a tick for each month here, right? On your timeline. We don't want to do that, and we don't have to. We have the tools to solve that problem, but it's not very efficient. So that's what this chapter is showing you, is that, okay, there's actually a more efficient way and a more efficient calculation that we can use. But in terms of the timeline, what I want you to do is I want you to show just 3 ticks usually is enough. Okay, so to indicate that you have an annuity, I want to see 1, 2 ticks, and then a last tick, and then you can use ... in between. Okay, so maybe here 1 month, 2 months. If I'm making monthly payments, right, for 5 years, what's my 5 times 12, so I have 60. So then 60 months, which means the second to last one is at 59 months. Okay, and then I ... in between. Okay, underneath, you're going to have the payment amount, PMT, PMT, PMT. Notice that there's no payment today. If you sign up today, then a month later, you have to make a payment. 2 months later, you have to make a payment, and then all the way up to the very end. Okay. And so what we do to show our calculation here, and maybe I should use a different color. Okay. If we are paying off a car, for example, right? Remember when we were talking about money coming to you and leaving your hands in terms of the calculator, because we will be able to use the calculator functions. And this is where the calculator really shines, right? Is when we have these crazy regular payments, okay? But what we can find is we can kind of funnel all these together, and then we can say, okay, all of these payments have some present value today, right? Or if you're saving for a car, right, and you are putting money into the bank, right, then the other option is that these payments are going towards some future value in 5 years from today, right? And so N here, either way, N is the number of payments now. Okay. So N is the number of payments. Okay. That's important because N used to be the number of compoundings, right? And so really what happens is when we have regular payments, N is the number of payments, right? So N is the time times F2. Okay. And I is I2, which is 1 plus I1 to the power of F1 over F2 minus 1. right? And so now the frequency is going to be F2. Well, all right. We're going to start by solving for the future value, and then we'll do one solving for the present value. So I should have introduced them in the right order, but that's okay. Where's the formula sheet? So what we want to do is, and maybe I'll, right, depending on if you want to solve for the future value or the present value, notice that in the future value formula, we're used to seeing the present value, right? But usually what happens if you're finding a present or a future value, then you're starting with nothing, right? And so you don't want to incorporate that. And then in terms of a present value, if you're paying off a loan, for example, then the loan amount is the present value, and then these payments are paying it off. Yeah. Very kind of similar looking calculations, but of course, kind of the order is reversed, right? And so here, where I is going to be I2, and N is going to be the number of payments. And PMT is the payment amount. Okay. So, and let's see here. PMT is the amount of each payment. And you've solved, you've solved problems where you have unknown payment amounts, right? And then you use X, but what if you have to solve for 60 of them? I don't want to do that, right? And so, and neither do you, I'm sure. And so now we have this more efficient formula that we can use. Okay, so let's do an example, right? Because depending on if you want to find the future value or the present value, that's going to determine which formula to use, right? So it's going to be super important that you keep track of which one you want. All right. So let's see here. I'm going to do example, I think it's, 204. Martha contributes $10,000 each year to her RRSP. At a rate of interest of 7% per year, how much will she have after 25 years? Okay. So let's start by just kind of highlighting all the information that we have, okay? Because now this is going to be slightly different than before. So she contributes $10,000 each year, which means the payment amount. So the PMT is $10,000. Okay. The payment frequency is 1, right, each year. So then what we're going to have is we're going to have F2 is 1. Okay. So the payment frequency is F2, okay, which is going to turn into the active frequency, right? Because we get rid of the compounding frequency, but I want you to start using the F2 for the payment frequency. At a rate of interest of 7% per year, so 7%, so R is 0.07, and the per year is compoundings per year, so F1 is 1. In this case, F1 equals F2, so I don't really need to adjust my compounding frequency, but I will, just to go through the motion and to get you in the habit of solving for I2 first. And so then time, how long will she have, or how much will she have? Yeah, T is 25 years, and we want to find the future value. All right, how much will she have after 25 years? So first, let's look at what the timeline looks like. Okay. I always fill up my page, makes it nice and clean. So let's say Martha starts today, and then for 25 years, she makes contributions. So at the end of each year. So like I said, for these timelines for annuities, right, if I'm making $10,000 payments, I don't really need to put 25 ticks on here, right? Because that's what it would look like. I don't want to, I don't feel like it. So after 1 year, oops, 1 year, 2 years. So what I've said is, okay, as long as you put the first two and the last, or the second to last one, then I'm happy. So then 24 years, the payment amount, let's match the colors here. 10,000, 10,000, 10,000, 10,000. So we want to find what the future value is. And remember that N is the number of payments. Okay. So here, N is time times F2, which is equal to F1 in this case, but just get in the habit of changing that. So now it's 25 times 1, which is 25. We're going to solve for I2. Okay. I2, which we don't technically need to, but it's safer this way. You'll see why. 1 plus I1 to the power of F1 over F2 minus 1. 1 plus, and it was 7% per year, so 0.07 divided by 1 to the power of 1 over 1 minus 1. So we get I2 is 1 plus 0.07 to the power of 1, then minus 1. Now this 1 minus 1 cancels, so I2 is 0.07. Okay. In general, if F1 equals F2, then if I2 is equal to 1 plus I1 to the F1 over F2 minus 1, if F1 is equal to F2, then that exponent becomes 0. So then I2 is 1 plus I1 to the power of 1 minus 1. So then I2 is equal to I1, right? That's just the case in general. But like I said, until you start to see that and say, oh, I can skip that part, safer to just always calculate I2. So that's what I'll be doing. Okay. So we want to find the future value, right? Because she's earning interest, right? So that's what's important here. And the whole point of you taking this course is to recognize that $10,000 a year from today is not $10,000 25 years from now, right? It's $10,000 plus interest, right? $10,000 plus 23 years of interest, $10,000 plus 22 years of interest, right? And so they're all earning interest, and you could draw them all different arrows, but you don't want to do that. We have a formula for that. So, oh, thought I had the formulas. So we want to find the future value. And we have all these components, right? Making sure that I is I2 and N is the number of payments. And so now the future value is the payment amount, 10,000, big square brackets, times 1 plus I2, which is 0.07, to the power of N, which is the number of payments, 25, minus 1 divided by I, which is I2, which is 0.07. So, if you're using this Desmos calculator, then you're safe to just do everything in one go, as long as you're very careful about your brackets, right? Otherwise, if you are not, you would start with this 1 plus 0.07 makes 1.07, then raise that to the power of 25, then subtract 1, then divide by 0.07, and then multiply by 10,000, right? That's the order of operations. But in terms of using this calculator, as long as I use my brackets carefully, I'm going to be super careful here. I'm going to put another bracket, 1 plus 0.07, close that bracket, to the power of 25. Step it down, close that bracket because I want that all to be in one value, then minus 1. It doesn't need it, but and then close that bracket. I'm almost tempted to have another bracket in here. Why? Because I want to force the 1 plus 0.07 to the power of 25 minus 1, all divided by 0.07. So you know what? I'm going to do it. I'm going to add in a bracket here and then close that bracket divided by 0.07. As long as you're careful, right? It will recognize, so I'll do it again less carefully. 1 plus 0.07. I think if I just do it as it shows, aha, I knew it. So this is where you'd want to be careful, right? You want the minus 1, but then all over 0.07. So that's why you need that bracket there. Okay, so it didn't work, but I think, well, it does work because of multiplication, but I'm actually going to clear that one. Because I want you to be careful with your brackets. So after 25 years, Martha's going to have $632,490.38 if we round properly, right? And so here, let's kind of move this over. So then the future value in money is $632,490.38. Good. All right. Let's see here. Let's do another example. So this was finding the future value. I'll put it on a new page. finding the present value, what does that look like? So what does the wording look like, and how do we solve it? So our next example is example 210. We do pretty much the same thing, except now things are going to get pulled backwards to today. Okay. Hank borrowed money from Tank. I love this question. Hank agreed to make yearly payments of $2,500 for 12 years. If Tank charges interest at 13% compounded annually, what was the amount of the loan? Okay, so the amount of the loan is the present value. Okay. Whenever you're borrowing money, that amount is the present value of the loan. Okay, so the payment amounts, PMT is 2,500. And the payment frequency, which is your F2, is yearly payments, so one time per year. And the time, T is 12, and 13% compounded annually. So R is 0.13 and F1 is 1. So here, once we get more comfortable, right, we're going to see that, okay, these are the same, right? F1 and F2 are the same. So I don't need to find I2. I can just use I1, or becomes the same thing. And so I don't need to do that. But before we do the timeline, let's just dig into it and find I2. I2 is 1 plus I1 to the power of F1 over F2 minus 1. I1 is 0.13 divided by 1. F1 is 1 divided by 1, which is F2, and then minus 1. I2 is 1 plus 0.13 minus 1. These cancel, so I2 is 0.13. Okay. And now the frequency that we're using is F2, which is 1. And the frequency we use is F2 equal to 1. Okay, because now that's the active frequency. So we can draw this on a timeline, right? So let's say Hank borrowed money from Tank today. Okay? And Hank agreed to make yearly payments of $2,500 for 12 years. So for 12 years, he's going to make payments. So 1 year from now, 2 years from now, remember the first two and then the second to last one is what I want as additional ticks on here. So 11 years. Okay. The payment amount is 2,500, 2,500. So put the amount, don't get lazy here. Put the amount under each of the ticks that I've made you do, right? You don't have to do all of them, so it's not that much to ask, right? But it does highlight that you're making these regular payments. Okay. We want to find the present value, okay, because we want to find the loan amount. So these payments are all being drawn back to some present value. Now remember, N is equal to the time times F2, which is 12 times 1, which is 12. Okay. So now for our formula, right? So far we've introduced these two, and so now I want to find the present value, which means what? The future value would be 0, right? Because if you have paid off the present value, then the future value after 12 years has to be 0. That's what we're forcing it to be, right? So now we can solve for this present value. So the present value is 2,500. Remember, it's the payment amount. Oops. Oops. 2,500 times 1 minus 1 plus I, which is I2, which is 0.13, to the negative n. So that's going to be really important because that's what brings things backwards. So negative 12 divided by 0.13. And if this is feeling like no fun, don't worry, I will show you how to use the calculator. And then the important thing is identifying all the key information that we're plugging into the formula, but you don't have to use the formula. It'll just do it internally, okay? And so, so you will be saved, but you should know how to use the formulas, right? So the present value, and you know what, I'll use the calculator right away. 2,500, being super careful with my brackets, right, is going to be 1 plus bracket 1, or sorry, plus minus bracket 1 plus 0.13. Close the bracket to the power of negative 12, making sure that negative 12 is all in the power. Then I'm going to close the bracket around, oops, but step it down first. There. And then I can divide by 0.13. Close the bracket. Okay. So the initial amount of the loan is 14,794 and 12 pennies. 14794.12. We can also answer things like how much did was it Hank who borrowed money? Yeah, Hank borrowed money from Tank. So an additional question that we could ask is how much interest did he pay? Right? So he's making payments of 2,500 and the initial loan amount was 14,794 and 12 cents. So that's how much he borrowed. So another question is, how much did Hank pay in interest? Right. The total paid is 2,500 times 12 years, right? 2,500, let's see here, times 12 is 30,000. Yikes. Right, why do I say that? Why do I say yikes? So he paid 30,000 to borrow less than half of that, 14,794. And so the interest paid is the total paid minus the present or the loan amount. Which is 30,000 minus 14,794 and 12 pennies. How can I make myself another line here without making too much of a mess? Just need one more line. One more line. Minus the previous answer, 15,205.88. That's not very fun, right? 13% interest will do that to you. Oof, all right? So pretty bad. So that's how we calculate the future value and the present value. And I'm hoping today I'll have a chance to show you how to use the calculator. If not, you'll have to wait until Wednesday, but it's good to do these by hand for a little bit. And then you appreciate the calculator more. Section 6.3, just like before, right? We just go through and calculate each of the components of the formulas. And so now we're going to talk about calculating the periodic payment. Oops. And number of payments which is N. Okay. So calculating the payment amount and the number of payments. Okay. So we're going to start by solving, so talking about solving for PMT. Let's start there. All right. Formulas. Okay. There is no formula, and remember, we're sticking to the left-hand side of the formula sheet. There's no formula for the PMT, but what we do have is we have these two formulas, right? And so because I could solve for PMT here, but I don't really feel like it. That looks terrible, right? And so I don't want to work with those. So here, depending on if you have the future value or if you have a present value, right, that will determine which formula to use. Okay. And so solving for PMT, right, we're just going to, oops. I guess I didn't grab them. Copy. Okay, so solving for the payment amount here. Okay. But depending on if you have the future value or if you have the present value, right, that will determine which formula to use to solve for PMT. Okay. So depending on if we know FV or PV, we will not know both, right? It'll be one or the other. We select the appropriate formula. and solve for PMT. Okay, so if you know the future value, then you use the future value formula and you can just rearrange everything and solve for PMT, right? And same thing, if you know the present value, then you can solve for this and solve for PMT. Okay, so let's do an example. We'll do example 212. Okay. Your RRSP goal is 300,000. Now, it's a little bit tricky in the beginning, right? Is this a future value or a present value, right? In general, if it's a loan amount, then it's a present value and then you're paying it off, right? If you're saving, right, then so an RRSP goal is going to be a future value. Okay. And so here, let's just say that the future value is 300,000. The current interest rate for RRSPs is 8% per year compounded annually. Okay. So here, R is 0.08 and compounded annually, so F1 is 1. You intend to retire in 30 years. Okay, so you're going to make payments for 30 years. So T is 30. How large should your year-end contributions be? Okay. So year-end means that F2 is 1. Okay. And we want to find PMT. So how we're going to show this on our formula, or on our timeline rather, is, well, first things first, let's just calculate I2 so we get that out of the way. I2 is 1 plus I1 to the power of F1 over F2 minus 1. Luckily, F1 and F2 are the same. 1 plus 0.08 divided by 1 to the power of 1 over 1 minus 1. So many ones. I2 is 0.08. Now F equals F2, which is 1. Right. Okay, so let's say you start saving today and you're going to be retiring in 30 years. And your goal was to have 300,000. Okay, so you're forcing this future value to be 300,000 at 30 years. So you're going to make year-end contributions. So after 1 year, you're going to make some payment amount. After 2 years, you make some payment amount. At 29 years, you're getting pretty excited. You're making your second to last payment. And then you do make that final payment at the 30-year mark, because they're year-end payments. But these are all going to funnel into a future value of 300,000. Okay. Now, N is time times F2, which is 30 times 1, which is 30. Okay. So I have a future value. So I'm going to use that future value formula. All right. So from here, right, I'm going to use this formula, and then I'm going to plug everything in and solve for the PMT, because that's what I'm looking for. Okay. Let's see. We'll just grab it fresh, copy. So the future value, we're forcing it to be 300,000, which is going to be the payment amount, which is what I'm solving for, times 1 plus I, which is going to be your I2, which is 0.08, to the power of n, which is the number of payments, which is 30, then minus 1, then divided by 0.08 I2. So what you want to do if you want to solve for PMT right away, right, is you can find that value, that 1 plus 0.08 to the power of 30 minus 1 divided by 0.08, and then divide that over to the left-hand side, right? And so whether you want to solve for that value first or just solve for it here, it doesn't matter. We'll get to the same place in the end. So it's going to be 30,000 times 1 plus 0.08 to the power of 30 minus 1 divided by 0.08. So now I'm ready to. So I've got 300,000, 1, 2, 3, divided by bracket 1 plus 0.08, bracket to the power of 30. Just make sure it looks the same way. Step it down, minus 1. Let's see if I close that bracket. Yeah, then the denominator, 0.08. Out. Oops. Oops. So what does that mean? Your payment amount, your annual payment amount must be $2,648.23, right? If you pay that every year for 30 years, in the end, at a rate of 8%, which is kind of wishful thinking right now, but then you would have 300,000 in 30 years. Pretty good, right? How much would you have earned in interest? Right, so always think about, so a follow-up question is, how much interest will you have earned? Well, if I save 26.48.23, or if I pay 26, so the total paid is 26.48.23 times 30. So take the previous answer times 30, 79,446.90. But I have 300,000, right? Because the rest is interest. So interest earned is 300,000 minus 79,446.90, which wait. One, two, three, minus that. 220,553 and 10 pennies. 220. Pretty good, right? Because that first payment that you make And each payment we found was 2,648 and 23 pennies, right? So 2,600 roughly, right? So this 2,648 sits there for 29 years, earning interest, right? Then 2,648 sits there for 28 years, earning interest. And so that's how you have so much interest earned, right? So kind of fun. Not as fun if you're paying it off, right? If you borrowed it and you had to pay that much interest, all of a sudden it's not as cool. Let's do you know what? Let's do example 213. I just have to find it because it's not in that printout. So I'm looking for example 213. I think. Let me just find it. There's Martha. Okay, here it is. So here, right, we were given the future value and we had to solve for the payment amount. So in this next one, I want to give you the present value and you have to solve for the payment amount. And maybe I'll just bump it down a little bit more. Okay. So if you buy a house for $401,000, okay, sounds nice. I can't really find that anymore. And you take out a mortgage, of course. So you're borrowing this money, right? Which means that it's a present value, right? So here, now we have this present value is 401,000. So you take out a mortgage to pay this off. The rate of the mortgage is 6.1% compounded bi-weekly, and you wish to make bi-weekly payments on your mortgage for the next 30 years. What are your payments? Okay. So the rate is 0.061 and F1 is, remember, bi-weekly is 26 times per year. That was one of those ones that's not as common that you might have to memorize or have written down somewhere, right? And so bi-weekly is a frequency of 26. Okay. And you're going to make bi-weekly payments. So F2 is also 26 and for 30 years, T equals 30. And you want to find what are your payments. We have the tools to solve this, right? I just don't want to use the old methods. I want to use this new snazzy formula that we have. But first things first, let's just find I2. 1 plus I1 to the power of F1 over F2 minus 1. 1 plus 0.061 divided by 26, right? So now it's no longer 1. So we do have to do work, right? 0.061 divided by 26, but then 26 divided by 26 minus 1. Okay. 26 over 26 is to the power of 1, so nothing happens there. But then what we get is 0.061 divided by 26, right? this 1 and this -1 cancel. And so we get I2 is 0.061 divided by 26. I'm just going to see if that makes a nice number. I don't think it does, but I'm just going to see if it does. If it doesn't, I'm just going to keep it as a fraction. 0.061 divided by 26. Okay, it doesn't. So I'm just going to keep it as a fraction. Okay. Or if you use the store function on your calculator, right, then I would maybe write down store 1 or something like that. Huh? So what does the timeline look like? For 30 years, so if we buy a house today and we're going to pay it off for 30 years, okay. And I'm going to write something above the 30 years, so I'm going to bump it down just a smidge. Tricks of the trade. All right. So every 2 weeks, okay. So 1 biweekly payment, 2 biweekly payments. And so now 30 years, how many biweekly payments have I made? Well, my trusty calculator, 30 times 26, I've made 780 biweekly payments. Okay. So this becomes 30 times F2, which is 30 times 26, which is 780 biweekly. Which means the second to last one is 779 biweekly, right? Because when I draw my timelines, right, I want the first 2 after today, and then the second to last one and the last one. That's all you need to show me. You're welcome to show more, but there's no reason to really. And we want to find the payment amount, PMT, 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 PMT. And these are all going to pay off, right, with interest, the present value of, and I should write down the number instead. I just made this arrow too long. 401,000, which is the present value. And then here I have N is 30 times F2, which is 780. I've already shown the work, so we don't need to show it too much again. Okay. Since I have the present value, right, then I need to use that present value version of the formula, right? Because what would the future value be? If I borrow 401,000 and I'm going to pay it off in 301,000, how much do I owe at the end? 0, right? So that's how it works. So we were told we have 401,000 is the present value. So then I have the payment amount is 1 minus 1 plus. Now remember the I didn't simplify it, and I don't want you to round it either, okay? Because if you round it, it can make some severe changes that you don't want in your calculations. Divided by, oops, I, which is 0.061 divided by 26. Okay. Or if you want, right? I'll do it differently this time. You can solve it like we did here, right? Just kind of swing things around before you substitute in, right? Solve for PMT by dividing this side over to the left-hand side. But in this case, I want to show you the other way that you can do it is just solving for this side and then dividing it over, it's the same thing, right? But what am I going to do here? First thing I'm going to do is I'm going to label this I, and hopefully, I don't think I is reserved. So I'm going to use that and say I, equals, because then I'm going to be able to refer to I as a variable, is going to be 0.061 divided by 26. Okay. So now I have that I. So whenever I type I into my next formulas, then I'm going to be able to refer to it that way. Okay. So that's what I wanted to do. And then put this over here because I need to see. Okay. I have 1 minus 1 plus I. Okay, so it recognizes I. Oh, I see that it's kind of hung up there, notabilities. We'll see if it sorts itself out. Okay, but I see it's kind of lagging there. Not on my screen, but there. Oh, but I lost it. It just kind of took over. All right, I think it's happy now. All right, 1 minus bracket 1 plus I end bracket to the power of negative 780. And to get the negative, you can just use the minus. That's weird to me, but that's just how it works, I guess. Then we're going to step it down, and I'm going to wrap this up in brackets just in case, because then I'm going to divide by I here. Make sure that it keeps up. Okay. And then in my next step, I'm going to have 401,000 divided by that previous answer. Okay. Save. It's kind of lagging here. Okay. So then my payment amount is going to be 1,121 and 2 pennies, right? Bi-weekly, twice a month, okay, for 30 years, and then I'll have it paid off. Okay. So here, what I want you to notice, when the loan is paid off, right, the future value is 0, right? So that's why it doesn't appear in the formula. When the loan is paid off, the future value is 0, which is why it does not appear in the formula. Which is why it does not appear in the formula. Similarly, right, if we're saving some money for some future value, right, then we start with 0, right? Similarly, if we are saving money, right, which is a future value, right, we start with 0. We usually start with 0. So the present value is 0. Okay. Another kind of general note is that if you're saving money, then that amount is the future value. Okay, so the future value is often saved money, right? And the present value is often borrowed money. Yeah. And so I say often, don't let that kind of bog you down, right? Just as a rule of thumb, if you're saving money, then you are accumulating to some future value. And if you have borrowed money, right, then you've borrowed some principal amount and you have to pay it off until you're at zero, right? Zero owing. Okay? So often that's the case, but it's a good rule of thumb. Okay. Let's see here. What if we have to calculate the number of payments? So that's going to be N. How long is it going to take me to pay this off? All right. So if we go back to the start of this section here, right? Calculating the periodic payment, which is the PMT. So we saw how to do that. There's only two scenarios, right? I know future value or I know present value, and I can use those to solve for the payment amount. Now, same thing for the number of payments, right? So just like we did solving for the PMT, now we're going to solve for the number of payments, N. Solving for the number of payments, N. Or usually we're solving for how long is it going to take? Or finding how long will it take to pay off or save some amount, right? Is usually the type of problem that we're going to find, right? But first I need to find N and then I can find T. We've seen that before, right? But now we have slightly more complicated calculations for N. They're not too bad, but still. We're just chugging away through this formula sheet, right? And we're going to tackle these two as well today. Wow, crazy. Not crazy for me. I saw it coming. Crazy for you guys, probably. Okay. These look very similar, right? And so if you're looking at these formulas, what are some differences? Kind of spot the differences. Well, I have some natural log 1 plus I, and then the future value over the payment amount, and then the log of 1 plus I. The denominator here is the same. I have a negative here and a minus here, but really the only thing that changes is that here you have some present value and here you have some future value and then some present value, right? And so depending on, so the formula to use depends on if we know the future value or the present value. Okay. So here, in terms of the question, how long will it take to pay off or save some amount, right? And so here, the question would be, how long will it take? So let's just kind of jot that down here. How long will it take to save future value dollars, right, is going to be that question, right? Just in general, versus here, right? How long will it take to pay off the present value? How long will it take to pay off present value dollars? Right, so it's two different structures, right? Both of them are solving for n, we know that. And so same as before, we have to be really aware of what a present value is and what a future value is, right? And so that's why I want to kind of give you these general wordings. So I've got example 216 that I want to do. Copy. So knowing this that we just outlined up top here, right? If Maxwell borrowed $20,000 from Loan Shark Alec, right? We know that this $20,000 right off the bat is what? Is a present value, right? If we borrowed money, we have to pay it off, right? And so right away, we know that this present value is 20,000, okay? That takes practice, right? Seeing that right away, but that's where I want you to get to. Alec demanded year-end payments of $3,500, okay? And so the payment frequency, year-end payments, so F2 is 1. Notice that sometimes they emphasize if it's at the end of the year, right? Year-end payments, that's going to become important once we introduce beginning of the year payments in chapter 7, right? But for now, right, the PMT is 3,500. Each payment is 3,500. How long will it take to pay off the borrowed money, right? And so that those are all clues. So we want to find n, right? And ultimately we want to find time, right? N is the gateway though. If Alec charges 17% interest compounded annually, okay, so here, so R is 0.17 and compounded annually means that F1 is 1. Just to get in the habit, just like I was saying, let's find I2 first. All right, as soon as you have regular payments, just find I2, get it out of the way. I2 is 1 plus I1 to the power of F1 over F2 minus 1. 1 plus 0.17 divided by 1 to the power of 1 over 1 minus 1. So I2 is 0.17. That's easy enough. Now, right, because I have the present value, that's going to turn me towards the right formula, right? I have these two to choose from, right? N and N. Okay. I don't have the future value because what? The future value should be 0. Now, if you put in 0 here, it's not going to work. Okay, because it has nothing to go off of. How long are you taking to pay off 0? It doesn't have anything to work with. And so we need to use this formula here, copy. But we have all the components, so I'm ready to just kind of plug them in. 1 plus I, which is I2 now, 0.17, times the present value, which is 20,000, divided by the payment amount, which is 3,500, divided by the log of 1 plus 0.17. Okay. Can plug these in. So I have the negative natural log. I'm just going to try to type it in as it appears, being really careful. 1 plus 0.17 bracket 20,000 divided by 3,500. Close that bracket. Close that bracket, divided by, making sure that it looks the same. Now that negative in front of the numerator is allowed to drop down in front, right? So that's okay. And then divided by the log of 1 plus 0.17. No, something happened here. Oh. What did I do wrong? I used plus instead of minus. Let's fix that here first. Minus. Why did I react? Why was I able to catch that was wrong? Let's go back to plus. -4 payments. That doesn't seem right, right? So that's how I caught it. Okay. So it is minus, and that makes more sense. Okay. So what I'm going to do is I'm going to screenshot this, and then I'm going to fix my notes because that's clearly not right. Here, I'll pretend it didn't happen. Minus. There. Cheating. We have the same rules for n as we did before when we were solving for time. Now, technically, we should be rounding up, right? It doesn't matter what the decimal is because 22.01 payments isn't enough, right? You can't do 22 and say, close enough, right? Loan Shark Alec would say, you still owe me some money, pal. Right. And so then you're okay, fine, 22 payments, or sorry, 23 payments. Okay, so you always have to round up. However, because we're working with these Moodle quizzes and they're not programmed consistently, sometimes you might just want to use. So if it's not accepting the rounded up value, then just try it with the unrounded value. That's incorrect, but same as before. Sometimes it can't handle it. So then n is 23, right? Always round up. Right? I'd need 23 payments. So therefore, we would need to make 23 payments. How long is that going to take? Right? N is the time times the frequency. Now the frequency is F2, right? The payment frequency, because N is the number of payments. So then 23 is time times 1. So it would take 23 years. So it would take 23 years to pay off Loan Shark Alec for $20,000. That is not very fun. And you can do things like, how much did he pay in interest, right? So how much interest was paid? Let's just... So an additional question is, how much will, who was it? Will Maxwell have paid an interest? How much will Maxwell have to pay an interest? The total paid is 3,500 times 23, right? Oops. 3,500 times 23 is 80,500. Uh-oh, it's not looking good. And interest paid is the total paid minus the total borrowed, right? Uh-oh, that's where it doesn't look very good. For Maxwell, looks great for Loan Shark Alec. Consider a career in being a loan shark. Minus 20,000, right? That's how much Maxwell borrowed. Right? Maxwell borrowed $20,000, but in the end, after 23 years, he's finally going to be paid up, but he'll have paid $60,500 in interest. Barf. Okay. I think we'll leave it there. Or maybe let me see the examples. You know what? Let's do this example, okay? Just because we can. We've got the tools, why not? 6.4 is on ordinary general annuities. I didn't spend any time defining it, but ordinary is payments at the end. And general is when F1 does not equal F2. Okay. So, let's do that example. Because we know how to solve this. We've been doing all the steps to solve it already. So what we want to do is just see it in action, right? Because so far, all of our payment frequencies and compounding frequencies have been the same, but I said, that's not usually the case, okay? Suppose month-end payments, okay? And so we've got a payment frequency of monthly, okay? So month-end payments, so F2 is monthly, okay, of $300. So the PMT, the payment amount is $300. Are made on a car for 4 years. And so the time here is 4. If the rate of interest is 5% per year, so R is 0.05, but it's compounded quarterly, F1 is 4. Right, so notice here that these are not the same. So that's when we really need to pay attention. What is the value of the car? Let's see here. I had to borrow that money and then I'm paying it off, making it a present value, right? Again, something that's going to take practice and reading a ton of questions to try to figure out, okay, is that a present value or a future value, right? But if I'm paying off a car, then I'm paying off a present value. Okay. So first thing we want to do is find I2, which is 1 plus I1 divided by, or to the power of F1 over F2, then minus 1. I2 is 1 plus I1, which is 0.05 divided by 4. Now, how I always read the power is I'm going from 4 compoundings per year and moving to 12 compoundings per year, because I'm forcing it to compound at the same frequency as the payments, okay? And so here, I2 is gonna be, and maybe I'll clear all here, 1 plus 0.05 divided by 4 to the power of, and make sure that you stay in the power for 4 over 12. 4 divided by 12, right? Notice how it shows that it's all in the power. Then you have to step it down minus 1. Okay. And I'm actually going to store this as I2 equals, because now I have that and I've stored it as I2. Okay. And I'm gonna just bring that in here. So I get 0.004149, but you don't want to use a rounded value. You have to use all the decimal places, otherwise it'll be just slightly off. Okay? Now our timeline is going to look like this. So for 4 years, I'm going to make monthly payments. So after 1 month, 2 months, 4 years has how many months? 4 times 12, oops. 4 times 12 is 48 months. Okay. Which means the second to last payment is at 47 months. And today. And the payment amount is 300, 300, 300, 300. And these are all paying off. Oops. Some present value, which is what we want to find. Now, the number of payments we said was 48, right? And maybe I'll, is time times F2, which is 4 years times 12, which is 48, right? So it's really important that you're using F2 as your frequency now, not F1, right? Because when we found I2, now your compounding frequency is also F2. So now we can use the same formula. I want to find the present value. I have the payment amount. I have I, which is going to be I2. I have N, which is the number of payments. So here we go. 300 times 1 minus 1 plus I2 to the negative 48 divided by I2. $300 bracket 1 minus 1 plus I2. And it just kind of did that subscript. I didn't have to tell it to the power of negative 48. Step that down, close it, divided by I2. Let's see here. Okay, so here, just want to they're paying off 13,032 and 19 pennies, right? So that's how much the car cost. There, we did it. So next day, I want to show you how to use your calculator functions, because then you won't have to use these big formulas, but it's good to have a handle on it. So I'll post an assignment just for using the formulas, and then you'll be able to use the calculator after Wednesday. If you have any questions, let me know. Otherwise, I'll see you on Wednesday. I'm gonna stop this recording.